So just a little reminder. We said in the atom there are 3 types of particles. So we used to think for years that the atoms were the smallest building block of matter. But now we know even the atom itself can actually be divided up into even smaller pieces. So it has this little place called the nucleus. And again, remember, even that little speck I drew is way too big for how big it is compared to the atom. Because remember, the atom is 100,000 times bigger than the nucleus. Well, which particles live in the nucleus? Remember? Electrons. No, not electrons. Protons. And what else? Neutrons. Okay, great. And the electrons do what? Yeah, they kind of orbit around here, right? So they're flying around here. And again, they're kind of zipping around here, right? And those are in the nucleus. Now we said though, which particles though have the most mass out of those 3? Which are the heavier ones? Which are the lighter ones? Remember? Pardon me? What'd you say? Yes, yeah, the ones in the nucleus are what? Those are the heaviest, right? Right. So the protons and the neutrons, we said, are around 1,800 times heavier than the electrons. Yet they live in that little tiny speck, right? Right. So we were saying last time, remember, the nucleus has so much mass in such a little space, it is incredibly dense, right? Remember we said it was crazy, crazy dense. Okay. Well, the thing that makes an element is this right here, right? The number of protons. You said so carbon is carbon because carbon on your periodic table has 6 protons, right? That's the thing that makes carbon carbon. If you change the number of protons, now you have changed carbon into something else. That's called transmutation. We'll actually get to that in the last chapter of the semester, which is called nuclear chemistry. But normally, yes, in a regular lab or factory, yeah, you can't turn an element into something else. So that's what makes it the element. But neutrons you can change, electrons you can change, everything else you can change around. So now when you change neutrons though, that's when we're making different isotopes, we said, of the same element. Okay. I'll show you in a second here. So I finished up right here, right? So yeah. So go ahead and pull up your periodic table if you don't already have it out there. And again, if you would, make sure you have the one that I asked you to print and bring so we're all using the same numbers, because especially in a week or two, some of the masses on like this one versus the one that Mariella has. Mariella has. So Marley's. Oh no, wait. Oh yeah. Oh, that's the same one. Oh, that's the one. Okay, yeah. Because those will be same numbers, but yours numbers will vary some on yours, Marley's. Yes, you want to get the same one. Okay, so we discussed that number above the element symbol. That's called the what? Atomic number. And that's the number of protons. Okay. And the number under it. So for example, on carbon it says 12.01. What is that number? That's the atomic mass, right? Okay. So let me look here. So what are isotopes now? So we're heading there. So I said, can't change the protons, but you can change the neutrons. And when you change the neutrons, that's when you're making isotopes. So for example, I could have several atoms of carbon, and they're all going to have 6 protons, but they might have different numbers of neutrons, which means they're going to have different masses because most of the mass comes from protons and neutrons. So, for example, hydrogen just normally has 3 isotopes in nature. So when you just grab some hydrogen out of the air or whatever, you're actually grabbing a mixture of isotopes. Now they're all hydrogen, they all have 1 proton, but they have differing numbers of neutrons. So remember last time we talked about, I showed you, when you're doing this number here, right? Oops, wait, they're not drawing for me. Try that again. This number here, that's the atomic number, right? That's the protons, remember? Didn't we discuss that last time? What's this number up here on top? That's called the mass number. That's the protons and the neutrons, right? Remember? Okay, so they're all hydrogen, so they all have 1 proton on the bottom, right? The difference is they're different isotopes, so they have different numbers of neutrons. So hydrogen 1, we would name that hydrogen 1, must only have 1 proton and no neutrons, right? Because it's got 1 proton, and that on top is protons plus neutrons, so it must be 1 plus 0. Are you with me? So that must have 0 neutrons. Hydrogen 2, well, that must have 1 proton and then 1 neutron, right? And hydrogen 3, well, must have 1 proton and 2 neutrons. So again, they are all isotopes of hydrogen. They're all hydrogen. So they will all so they will all react just like hydrogen. So hydrogen 1 reacts the same as hydrogen 2, reacts the same as hydrogen 3. The only difference is this one weighs a little more than that one. This one weighs a little more than that one. Weighs a little more than that one. Are you with me? Yes.
Now, can these be changed only by man-made stuff, or kind of like nature change the amount of neutrons or atoms?
Nature can do it as well. That's what we're going to get into in the last chapter, which is all about radioactivity. And radioactivity is normally actually when one isotope is turning into a different isotope. That's actually radioactivity. We'll see that later on. So these, by the way, just FYI, have special names. Hydrogen 1 we call protium because it's just a proton. That's all it is, right? Hydrogen 1, all it is a proton. There's no neutron, so we call it protium. Hydrogen 2, I'm going to write it up here so you can see it a little easier. This one you might have heard of, called deuterium. Ever heard of deuterium? Anybody? No? That's okay. But hydrogen 3, I bet a few of you heard of hydrogen 3. It's called tritium. You ever heard of tritium? Anyone ever heard of tritium? No, never heard of tritium either? Okay, so tritium is a radioactive version of hydrogen, and it glows in the dark green. It used to be used a lot on like watch faces. On watch faces, they would take a little bit of tritium. They would kind of like paint the dots on your watch, and it would glow green at night. And the military actually, they still use it on their gun sights sometimes. So they have like a little dot of tritium on their gun sight, and then at nighttime they have a little green dot where they're sighted, and they can still see it in the dark because it glows green. So that's tritium. Now, again, I said the difference in deuterium versus hydrogen reacts exactly the same way, but it weighs about twice. Can you see that? Because remember, protons and neutrons, the mass of those two is roughly the same, right? So this one's going to weigh about 1, but this one's going to weigh about 2, right? So what you can do then with hydrogen is you can make this very interesting stuff called heavy water. Ever heard of heavy water? Anybody know what heavy water is used for? Okay, well, heavy water. So again, normally water is just H2O, right? Right, that's water, H2O. Well, most normal water is made with just hydrogen 1. So, just normal water. But if I were, instead of use hydrogen 1, if I were to use hydrogen 2, well, hydrogen 2 weighs more, right? I just told you that. So it would be heavier. So if you make it with hydrogen 2, that's called heavy water. And heavy water is used a lot in nuclear power plants. So one of the things that happens when you're trying to generate nuclear power, and we'll see this again once we get to chapter 4 at the end of the semester, nuclear power plants. And one thing that happens is in nuclear reactors, what you're doing then is you have uranium, and the uranium is undergoing radioactive decay, and it's spitting out neutrons. And those neutrons then fly out of the uranium, and they strike other uranium, which causes more neutrons to fly out, and it just keeps happening over and over and over and over, and it makes more and more energy. But the speed of the neutrons normally, though, was way too fast for them to actually slow down enough to actually hit a uranium and cause a reaction. So they have to be slowed down. So what they'll do a lot of times then in nuclear power plants, they'll use heavy water, kind of like the medium, So they'll have the big rods over here. Oh, why is it not drawing? Okay, so they'll have a big rod with uranium, and then around that they will put water all around it. But the water they use is heavy water, and then the neutrons, as they fly out, they kind of slow down going through the heavier water. So back in World War II, then, both the Americans and the Germans, were both trying to make nuclear bombs. And one of the things that they needed was heavy water so they could make nuclear reactors to make uranium. So the Germans really wanted to get heavy water. And one of the only surviving factories that made heavy water was in Telemark, Norway, which was neutral during the war. So the Germans tried over and over then, back in World War II then, over and over then to try to invade Norway so they could get their hands on heavy water so they could make their own nuclear bombs, was the thing. So I read a story one time, and actually there's a movie about this too. It's called The Raid on Telemark. I've never actually seen it. There's a whole movie on this because the Allied forces, I can't remember, I think it was 4 special forces teams, special forces teams, 4 actual British SAS special forces teams over to Telemark trying to blow up this nuclear power plant, just so it wasn't a nuclear power plant, but a heavy water factory in Norway, so the Germans wouldn't get their hands on it. So they tried 3 times, everybody died, but finally on the 4th time they actually destroyed it. So it was the most important special forces raid in all of World War II, this British SAS team that finally blew up the heavy water plant in Norway, which stopped the Germans from getting the A-bomb, which probably would have been a bad thing. So anyway, so that's heavy water. Well, why is it heavy? Because it's not made with regular hydrogen. It's made with hydrogen 2, which again weighs about twice as much as hydrogen 1. So that's what's called heavy water. Okay. So real quickly, I have 3 different isotopes here, and I just called them all X. So which of these would be isotopes of the same element? 1 and 2, 1 and 3, or 2 and 3? Which are the same element? 1 and 3, how do you know?
Same protons.
The bottom number, right? So that's what makes them the same, is the number of protons, right? So even though that's X31 and X32, same element, just different number of neutrons. So these two, though, even though they're both 31, they're different elements, right? Because they have different numbers of protons. And the protons are what makes the element the element. If you change the protons, you turn it into something else. Okay, so B. What's the identity of that one? What is that element? Somebody tell me. Find your periodic table. What is that element? Sulfur, right? How do you know? Just find number 16 on your table, right? It's number 16. Right, good. So that's sulfur, right? So that's sulfur 31. That's sulfur 32. What's the middle one then? Number 15, right? So it's phosphorus 31. Yeah, right, good. Yeah, so B is sulfur, right? Sulfur, S, sulfur. Okay, good. Okay. So normally then, again, we try to distinguish between different isotopes is the mass number, right? Because that's the thing that makes them unique. So, for example, this one here, this is nickel with a mass number of 61. So I would just name that nickel-61. Okay? So it could be hydrogen-1, hydrogen-2, or name it as nickel-61. Now, oftentimes, though, we don't even write in the number 28 there. So you may even just see it written like this, nickel-61. Why is the 21? Why is the 28 not always written, do you think?
It's already defined.
Yeah, it's nickel, right? So nickel is always number 28. Does that make sense? So if it's nickel, it has to be 28. So oftentimes we don't even write the 28 just to save time. We'll just write nickel with the little 61. That makes sense? So nickel's 28, right? Oh, it's nickel. It has to be 28. Does that make sense? Okay. So for example, here's another one. Carbon-14. You might have heard of that. Carbon-14 dating, radiocarbon dating. Ever heard of that one? It's what like to date things that are old, paintings or artifacts. So that's carbon with a mass number of 14. It's still carbon because it has 6 protons, right? So how many neutrons would carbon-14 have then?
8.
14 minus 6, right? It must have 8 neutrons. Right. Yeah.
So I was wondering how come it's written the opposite as on the periodic table. Like top and bottom, the mass and the number of protons.
Okay. Yes, good question. So she's asking, okay, so she's saying nickel, its mass is about 61 on there, is that what you're saying? Or you're just saying why is the 28 on the bottom, not on the top?
Yeah.
I don't know exactly. I don't know. Yeah, I really don't know, I guess, why that convention was chosen. I'm not really sure why they chose to put on the top and not the bottom. I don't know. Sorry, I don't have a good answer for that one. Okay, so how about this one? Lead 206. How many protons are in lead 206? Give you a hint, it's not 206. How many protons are in lead 206? How many?
46.
No. Find lead.
Protons?
What's lead's symbol, first off? PB. So PB is number 82, yes. So it have 82 protons, PB, which means if it has 82 protons, how do you find the neutrons? So take 206 and subtract 82, so how many neutrons would it have? How many? 124, right? 206 minus 82. So, again, protons are easy to find. You find it on your periodic table. The neutrons, subtract it from the mass number. Oh, that's not anything. Questions? Okay. Good. So let's try another one on your handout. So, okay. First one I'll do with you. How many protons and neutrons does an atom of nitrogen 15 have? So, how many protons would nitrogen 15 have? Nitrogen 15 would have 7, right? You find it there on your table. Has a big number 7 above it, right? Well, how many neutrons must it have? 15 minus 7, 8. And I'm going to write the little symbol for neutron, right? N with a little 0, because it has a 0 charge. Okay, your turn. Try B and try C, then we'll talk more with your neighbor and see what you guys think. Okay. Okay, talk it over with your neighbor. What do you think for cobalt 60? Again, it's used in cancer treatments like gamma knife surgery, they call it sometimes. What do you think? Ask your neighbor. How many neutrons are in that? Okay, and how would you, you're right, so B is how many? What'd you say? 33 neutrons. 60 minus 27, right? How would you name that little symbol there? Absolutely. You would name it uranium hyphen 235. Right? Uranium 235. Okay. Let's try this one. I like this one. Okay. Let's do the first couple of columns together here. Okay, so we're going to do the columns here. We're going to fill in the columns as go down here. So, the symbol is, what is CR? Crapium? Oh, what is it? Chromium 52. Okay, so chromium 52. How many protons are in chromium 52? So find it on your table. What is it?
24.
It's number 24, so 24 protons, right? How do we find the neutrons? Subtract that from 52. So how many neutrons would it have? 28, right? So we take 52 minus 24. Good. How about the electrons? What did we say last time about the electrons? How do we find that one?
If it's neutral, then it's be the same.
Yes, it's neutral, so it is the same as the what?
Protons.
Right, so protons are positive. So if it's neutral overall, then it must have the same number of negative electrons. So if it has 24 positives, it must have 24 negatives. Remember that? And what's the mass number down here? What do I write down here? Proton. Yeah, this thing right here, right? 52. Right? Okay, let's try the next one together. 25 protons and 30 neutrons. Okay, so how many electrons? Let's do that one first. How many electrons? 25. Why? Again, it's neutral, so if it's got 25 positive protons, it must have 25 negative electrons. Okay, what's the mass number I will write down here? Sorry? 55. 25 plus 30, right? 25 protons plus 30 neutrons, so 55. So what isotopic symbol would I write up here at the top? 55, and it's what is it? Mn. Oops, manganese. Come down here. Manganese 55. Perfect. Oops, okay, your turn. Try the next 3 columns there, see what you get. Fill in the next one. 64 neutrons, 48 electrons. What can you figure out? Okay, go ahead and compare just the next column with somebody. Just the next column with somebody. Not all 3, just the next one. Let's make sure you're on the right track first before you go crazy. So just compare column 3 with your neighbor. Time out, compare column 3.
64, 100.
Find somebody. Maybe they're behind you, maybe they're in front of you. Find somebody. Okay, well, once you agree, go on and do column 5 and 6. I mean, 4 and 5. Okay, go ahead and compare 4 and 5 then. Compare all the columns if you haven't. What'd you guys get for the next ones? You had the same symbols. What's what?
RN?
Radon.
It's close.
Radon.
For the chapter 3 test, what's it going to be consisting of?
Pardon?
The chapter 3 test, what's it going to be consisting of?
Chapter 3 quiz?
Yes.
Just everything on chapter 3, so all this kind of stuff. Protons, neutrons, electrons. All the stuff we'll do today and Wednesday, too. So, yeah, just all this on chapter 3. Okay, so let me start filling it in here with you. So, first thing I'll probably do is say, protons. Well, protons are pretty easy to find if it's neutral, because it's the same as the electrons. So I would put a 48 in there. Mass number, well, it's going to be 48 plus 64, right? So 112, is that right?
Yes.
And then what's the element symbol up here? What is number 48?
Cadmium.
Cadmium. A lovely heavy metal. Cadmium what?
112.
112, right. Okay, yeah. Yeah, cadmium, by the way, is what you use in NiCad batteries. Remember NiCad batteries? Use like I use a lot like in cameras and stuff. We'll say like NiCad battery. It's nickel, cadmium. That's why it's NiCad. But yes, it is a nice toxic heavy metal, so be careful. Okay. Next, let me see. So, again, the next column, the easiest one to probably figure out is the protons, right? I see 86 electrons. I can just go 86 right here. Neutrons will be 222 minus 86. So what's that? 136. Okay, so what symbol goes up here? Number 86 is Rn, which is radon. Radon what? Radon. Okay, and then next one, 82 protons. So I can do electrons pretty quick. 82. Neutrons is 207 minus 82, so 125. So what symbol would it be? PB 207. I'll try and squeeze that in there. Awesome. Okay, again, the protons are what makes the element, right? You can change the neutrons, we can change the electrons, but if you change the protons, now you have turned it into a whole new element, right? And we can only do that like in nuclear reactors and things, so we won't do that until later. Okay, now, I mentioned this last time. Mass number, which is protons plus neutrons, is not the same as that number written there then on your table underneath the element, right? That's the atomic mass, which is, again, is the actual average mass of an atom. So again, mass number is protons plus neutrons. It will always be just a simple integer. Atomic mass is the actual mass of a hydrogen atom. Okay, but it's not just the mass of any hydrogen atom, it's actually the average mass. So I just got done telling you then that not all elements are the same, right? You can grab some hydrogen in the air, and you're going to grab hydrogen 1, but you also might grab a little bit of hydrogen 2 or some hydrogen 3. So that mass then that's written there then, on your table under hydrogen, it's actually the average of the hydrogen 1 plus the hydrogen 2 plus the hydrogen 3. But it is not just a simple average where you just add them up all three and divide by 3, because it's not equally 1/3, 1/3, 1/3. It's what's called a weighted average. So we're going to use a little formula that looks like this. So write this down. Where the average atomic mass is just, this symbol here is the Greek letter sigma. It means the sum of the abundance times the mass of every isotope. So if there was 3 isotopes, let's say, of hydrogen, it would be the abundance of isotope 1 times the mass of hydrogen 1, plus the abundance of isotope 2 times the mass of hydrogen 2, plus 3 times 3. So it's the sum of all the different isotopes. The amount there is times the mass. That won't make much sense until we do an example here. So let's do an example. Okay, you got that written down? So the average mass, again, that's the number under the symbol on your periodic table, right? So carbon is 12.01. That's not the mass number, which is just protons plus neutrons. Again, which will always just be a simple integer. That number is the average of the carbon 12 in the world with the carbon 13 in the world. Okay, so for example, neon, right? So like neon signs. Right, I'll see neon signs. Right? Well, neon signs have neon gas. If you just go to any neon sign and you grab some neon out of that sign and you actually to analyze it, it's not all the same. Some of it's neon 21, some of it's neon 22, some of it's neon 20. It's a mixture of different isotopes of neon. So they're all neon, right? So they all have 10 protons, but some have 10 neutrons, some have 11 neutrons, some have 12 neutrons. Therefore, they all weigh a little bit. So in our case, for neon, most of it, 90.48% of it, is neon 20. You see what I'm saying? And then 9.25% of it is the green, neon 22, and 0.27% of it is the orange here, neon 21. So again, it's not all the same, right? It's different isotopes. Again, these have different masses. So, the number then, the mass that is written on your periodic table underneath neon there, where it says 20.18, are you with me? That is the average of hopefully stuck outside there. That's the average of 90.48% of it weighing about 20, 9.25% of it weighing about 22, and 0.7% of it weighing about 21. Okay. Here's the actual data. So, neon 20 has a mass of 19.9924. So, that number on your table is the average of this abundance times that mass, plus this abundance times that mass, plus this abundance times that mass. We add them all up. I can't just take all three, this plus this plus this, this plus this plus this, and divide by 3 because they're not equally a third, right? It's not like a normal average where you just add them up and divide by 3. It's called a weighted average. So, let's just try this. Let's take this and multiply it by that, plus this, multiply by that, plus this, multiply by that, and we better get whatever it was on there, 20.18. So, let me do that with you. And I just want to remind you, though, the most common mistake people make is they forget how to use a percentage when they start to do math. So, when you use a percentage in calculations, we always want to turn it back into the decimal form. So you always want to take that, you want to divide that basically by 100. So you wouldn't take 90.48 times 19.9924. What would you do? Do you know? Remember?
Wait, 904.
Yeah, so we would take 0.9048 and multiply that by the mass, 19.9924. And then I would do the next one. So how would I turn 0.27 into a decimal?
0.0027.
Yep, 0027. That one times its mass, 20.9938, plus the next isotope. So somebody else, 9.25. How would I turn that into a decimal? 0.0925. Again, so abundance times mass, and its mass is 21.9914. So try that out in your calculator, add it all together, and hopefully you'll get about 20.18, whatever the table said, right?
Can't you just, this is a little more complicated, can't you just multiply like 19 times a percent, like 19 times 90.48, then divide by 100 afterwards?
I don't know. Will that work?
I think so. At least.
I'm not sure. Okay, so you should get 20.18 if you did it. Is that what you got? And what unit do we use, by the way, to measure the mass of these little tiny things? What's our unit? It's not grams normally. Remember what it was? AMU. What's AMU stand for again? Atomic mass units. Yeah, so this is going to be mass unit. So again, so that's literally where those masses come from then on your periodic table. It's not just the mass of just carbon in general. It's the mass of as the weighted average depending on carbon in nature. So basically then in nature then with neon, you go here or go to Neptune or anywhere you want to. If you grab a sample of neon, it'll roughly have all of these same percentages, okay, wherever you go. Or carbon, right? You get some carbon sample out of a person, out of a plant, out of a tree, out of a rock, wherever you want to get it out of, and it'll always have roughly then, the same percentage and mass. So again, so that number for carbon is the average of carbon 12 in the world as well as a little bit of carbon-13. That's also naturally occurring. You average them together and you get that number 12.01 for carbon, for example. Okay, well, let's try another one together here. Let's try copper. So, copper, just, naturally occurring copper, you go mine some copper out of the ground, get a copper penny, copper wire, whatever. It's not all the same atoms. It's all copper, but some of it's copper 63, and some of it's copper 65. So the question says, if 69.17% of all of the copper has a mass of 62.9396, and the rest of it has a mass of 64.9278, what's the average atomic mass of copper? So try it out, talk it over, help each other out. Same thing, it's abundance times mass plus abundance times mass. So talk it over, talk it over. First thing you got to figure out is what's the other abundance, because it's not given to you. So talk it over. How do you figure that out? Okay, so did you get 63.55? Which is what copper is? It's 30.83. I think you must use 64 or something, but it's 69. There you go. Okay, did you get that? Okay, so let me just do it real quick with you. So 69.17% is copper 63. So how do I do 65? Oh, I'm going to take 100 minus 69.17%. So the total is 100%, right? If I subtract the copper 63, that leaves me 30.83% copper 65, right? Okay, so let's just do it out. So let's take 69.17%, but I'll turn it into a decimal form. So 0.6917 times the mass of copper 63, which was 0.9396 AMU, plus copper 65, which was now 30.83%, so 0.3083 times its mass, which was 64.9278 AMU. And yes, you get 63.55. Sorry about my messy writing, but 0.55 AMU. How'd you do? Awesome. A plus.
Was that the total?
Was that the total?
Yeah, the answer.
Yeah. The copper's atomic mass. Yep, it's the average of those two things. That's it. Okay, so try silver. Try silver. Try B. So again, we only got two isotopes. See what you can do. Well, again, those little specks are much smaller compared to the protons and neutrons, but they are hugely important because we'll see then that basically all the physical properties and all the chemical properties actually come from those little specks called the electrons that are orbiting the nucleus. So the reason silver is shiny and has a certain density and has a certain melting point and all the different properties it has is not really based on the protons and neutrons. It's based off those little minuscule specks called the electrons. Well, there was a very famous Danish chemist. He was from Denmark, Copenhagen, named Niels Bohr. And Niels Bohr, he was trying to figure out, basically, well, how do the electrons orbit in the nucleus? So right here's our nucleus, and we have the electrons, and they knew the electrons were out here somewhere. But the question was, what are they doing out there? Are they just going wherever they want? Just a free for all? Just kind of orbiting around, or not? And Bohr's speculation was they weren't just going wherever they wanted to. They weren't just free to roam. They were only allowed to roam in certain what are called orbits. So kind of like this. So he said, so some electrons are in the first orbital. Some are in the second one. Some are in the third one. So basically then his proposed model then was more like our solar system, right? Where the planets have kind of certain fixed orbitals, right? They're not just wandering all over the galaxy wherever they want, but they're staying in certain orbits around the nucleus, around the sun in our case, right? So that was his speculation, but he didn't really have any proof for that yet. That was his speculation. So these different little orbitals, these are called energy levels. So that first orbital is also called the first energy level, or n equals 1. The second orbital is called the second energy level, or n equals 2. So the one that's closest is the lowest energy. As they go farther away, they're going to have higher energy. So let's think about why is that for a second. Why do the ones that are farther away have higher energy compared to the ones that are closer? Okay. So, which particles live in the nucleus again? Protons and neutrons. So what is the charge on the nucleus? Positive, negative, or neutral? It's positive, right? Because it's got positive protons and it's got neutral neutrons, right? So overall, the nucleus is positive, right? Okay, so what's the charge on the little specks of the electrons orbiting around there? Negative. So I have these negative electrons out here, right? They're zipping around. So what happens between negative particles and positive particles? What do they do to each other? Opposites attract, right? Okay, so there is then a little bit then, not a little bit, but there actually is then like an attraction between this positive nucleus and these negative electrons, right? So there is an attraction between these. Are you with me? So there's like an attraction between these two. Okay, so this positive and negative attraction then is holding the electron in place. So it's not just flying off into outer space. When the electron then is here and it's closest to the it's here and it's closest then to the nucleus, it's going to have its strongest attraction, right? It's closer, so it's going to have a stronger attraction. Does that make sense, right? If they're stronger versus like far apart. That makes sense? With magnets, there's going to be a stronger attraction when they're closer together than if they're farther apart. So think about this for a second then. If I want to take this electron and I want to move it from here out to level 2, let's say. Okay, so I want to move it. Or I'm going to move it out to level 3. Well, that's going to take some energy, right? Because it has an attraction. I have to pull it away from that nucleus to move it out, right? I have to put in some energy. It makes sense. I have to pull it farther and then pull it farther. So that takes energy to pull it away. So this one is the easiest. It's the lowest energy. But to move it out to here, that's higher energy and higher energy and higher energy and higher energy the farther we go. So the lowest one, the first one, is the lowest energy. And then n equals 2 is the second lowest energy, or second highest, as you can think of it. And then the next higher energy, and they get higher energy. So as they go farther away, they have higher energy. Does that make sense? Yeah. Okay. So this is the lowest energy. This is the highest energy. And on up 6, 7. Yes.
Will the density of the nucleus affect how strong the attraction is?
not the density of the nucleus. I mean, it's not really the density. But there is an effect though on the attraction though, based off the number of the protons and the neutrons. Yes, that'll affect it, right? Because more positives, charges in there will have an effect on the attraction. Yeah. So, for example, right? For example, hydrogen only has one proton in the nucleus, right? It's number 1, right? So you might have 1 proton, versus helium has 2 protons, right? So you would have a stronger charge. So charge then from here to the electrons if there's 2 positives versus 1 positive. So yes, it will have an effect on all that kind of stuff. And actually, we'll see a little bit of that as we go on. Okay, so this was great, and Bohr won the Nobel Prize back in 1922. Okay, well, as I was saying this is all a great theory, but he had to kind of prove his theory. And the way he actually proved it was he was reading like a journal article one day, and he saw this study of these people, and they had been studying hydrogen gas. So, normally, change color here. So normally, let's say you have like a little prism. You know what a prism is? You have a little prism, and you pass light through it, and right, you pass some light through it, and then you get out what? A rainbow, right? Right. So you have, I don't know, the sun over here, okay? Some white light passes through it, and then you get out a nice big rainbow, right? So you get. Well, let me just do an order here. Red, right? Roy G. Biv, right? Oranges, yellows. I don't have a slide for this, sorry, but it is important, so I'm just writing it on here. Blues, indigo, and violet, right? Okay, so, and you get a rainbow like that, right? And you pass it through. So all light travels at the same speed, called the speed of light, which is c. So that's the speed of light. So all light, red, orange, yellow, infrared, ultraviolet, all light travels at 3.0 times 10 to the 8th meters per second. That's the speed of light. And you've all heard of that because you've all heard of E equals mc squared. And that c is the speed of light. Same c, speed of light. So all light travels at that same speed. Again, any kind of radiation, basically, gamma, microwaves, radio waves, television waves, infrared, ultraviolet, it all travels at the same speed. So what's the difference then in these different colors? What's the difference then is what's called the wavelength. The wavelength. So let's say I have a wave of red light, and it goes like this. So light, we now know, doesn't just go in straight lines. It actually has waves. So if I were to measure the distance of one wave, okay, I'm going to change color. Okay, so my wave starts here, and then it goes to here, and it stops, and then it starts again, right? You see that? How it kind of goes and goes. So that distance, that's what's called the wavelength. And we abbreviate that with a Greek letter lambda. That is the wavelength. Literally, the length of a wave. Okay? So the difference in red versus orange, it's not the speed, all the same speed, it's how long the wave is. Okay? So orange is actually a shorter wavelength than than red. And yellow is shorter than orange, and green is shorter, and blue is shorter, and violet is shorter. Okay, so they all have different wavelengths. So I might have another wave, let's say it was purple. Oops, I'm going to use black again just to be consistent. So it might look like this. Same speed, but now it has a very different wavelength. Do you see that? Right? So this would be the wavelength for this one. So much shorter waves. Okay, so that's one component of light, is what's called the wavelength. Now the flip side of that is something you might have heard of called the frequency. It's like in your radio station. It has various channels all right on your radio and all different frequencies. So it's 98.1 megahertz. That's a frequency. Well, that is literally how frequent is that wave passing a certain point every second. So frequency, we abbreviate that with the Greek letter nu, which looks kind of like a little V like this. The Greek letter nu in U, it's a little V. So that is literally, again, it's how frequent are the waves. So what you do then with frequency is you measure then. Okay, so how many waves then will pass a certain point? So let me go over here. Let me use blue. So let's say this is time 0 seconds, and let's say down here is, I don't know, let's say right here is time 1 second. Okay? So, in 1 second, on the long one, I get one wave, right? And then half another wave. Are you with me? But on this one, I get a lot more than 1.5 waves, right? This one I get, here's a wave, and here's a wave, and here's a wave, and here's a wave, and here's a wave. Right? Are you with me? So same speed, but I get a lot more of them. So you can see then as wavelength increases, the frequency decreases. Right? There's fewer waves passing your point every second. And as wavelength decreases, frequency increases. I will say that again because you're not writing it down. As wavelength increases, frequency is decreasing. Because again, longer waves, you may only get one wave every second, or you may get one wave every billion seconds, whatever it is. But if they're shorter, we can get a lot more waves in the same time frame. Wavelength increases, frequency decreases, vice versa. Wavelength decreases, they get shorter, well then your frequency increases. So here your frequency, let's say, is 2, and here it's 7, or whatever it is. I'm just making up numbers. Are you with me? You see what I'm saying? Okay. So, again, they're all the same speed. Well, how about the energy then? Okay, so how is the energy different of, let's say, purple light versus red light? Or let's say, I don't know, microwaves versus radio waves. Because they're all at the same speed, but the difference is in this wavelength, or the frequency. So the longer the wavelength they are, the lower energy they have. The higher the wavelength they are, the greater the energy you have. So the longer the wavelength, which means then the shorter the frequency, they're going to have less energy. But if they have a short wavelength and a really high frequency, then they have a high energy. So you increase energy as you increase the frequency, or as you decrease the wavelength. So you think about it kind of like this way then. Okay, yeah.
Sorry, can you say that one more time?
Okay, so you increase the energy as you increase the frequency, or you increase the energy as you decrease the wavelength. Because again, wavelength and frequency are always inverse. Okay, think about it this way. Okay, so let's say then you're down at the ocean, and the waves are coming in, right? Right. Let's say it's one wave every second coming in and it's smacking into you, right? Okay, so you're feeling the force of one wave every second, right? Now let's say there's 7 waves hitting you every second. Right? So it's more energy smacking into you. Does that make sense? So this one with a higher frequency and a lower wavelength has more energy than this one, which is a longer one. Are you with me? Okay, good. We are doing some Nobel Prize work here.
So the one at the bottom has more energy than the other one?
Yes, this one here, yes. Shorter wavelength, which means like I said, in 1 second, more waves then will actually pass your point, actually smack into you. So that's going to give you more energy. Okay, so in light, red is the lowest energy end of the spectrum. Let's use a good color here. What should we use? Let's use this lovely. So this down here is the low energy end. And purple, this down here, is the high energy end. So violet light has more energy in it than red light, for example. Okay, so let's go back to our little experiment. We'll see why this is so important. So again, Bohr had a theory then that electrons were not just going willy-nilly wherever they wanted to, but they were only living in certain orbitals. Okay? So Bohr, like I was saying, so Bohr, he read a paper. I'm going to do a bit of erasing down here. And he read a paper where some scientists, they had taken hydrogen gas and they had zapped it in with electricity, and they had taken the light off the hydrogen gas and passed it through a prism. So let me draw another little crappy picture here. So they had a tube, let's say, with some hydrogen gas over here, and this is hydrogen gas. And they zapped it with electricity. So they zapped it, zap. And that hydrogen gas, actually, hydrogen gas, actually see it in lab on Wednesday, gives off a pink light when it glows. It gives off a pink light. So when that pink light was passed through a prism, they did not see a rainbow. And they freaked out. They're like, what the freak? Why is there not a rainbow coming off this thing? What's going on? And instead, they saw only 3 lines. They saw a kind of like a bluish line. Oh, let me do this thicker one. They saw kind of like a teal green color line. And then they saw a red line. So they're like, wait a minute, why are we not seeing every possible wavelength? The Bohr said, I know, it's because of the electrons. Okay, so let's think about this for a second. Okay, so I have, let's say, right here, and I'm going to draw some more orbitals just kind of illustrate here, okay? This is n equals 4 or whatever. So let's say I have an electron and he lives right here, okay? Here he is, here's my electron. And again, this one here then, that's closest is the lowest energy state, you know, right? Okay, so I come along then here then, onto my hydrogen, and I zap it with electricity. So when I'm zap it then, I'm giving it energy, right? So I give it energy, and what's it do? Well, it has to move to a higher energy state. So maybe it jumps out to here. Or maybe it jumps out to here. Or maybe it jumps out to here. Whatever it does, right? So it jumps up there for a second, and then it falls back down. And then when it falls back down, it has to lose the energy. Well, the way that it loses the energy is as light. So it gives off some kind of light. Or, like I said, or it jumps to here, and then it falls back down, and that loses some light. It jumps to here, and then it falls back down, and that gives off some light. Well, the thing is, this amount of energy is smaller than this amount of energy, is smaller than this amount of energy. Are you with me? So therefore, 3 different energies of light. So you're going to get 3 different colors of light. Are you with me? Okay, so what if it had been this model? What if this model then was correct? Well, in this model then, the electron, say it was right here. Well, in this model then, if it's really free to go wherever it wants, it could jump anywhere it wants to and fall back anywhere it wants to. And you would have seen a total rainbow of every possible energy, right? Because it could have been here to here, or here to here, or here to here, or here to here, or you know what I'm saying? You know, every possible jump was possible. So you would have seen every possible color or energy, but you didn't. You only saw 3. So you said, aha! So there must only be certain energy levels allowed for the electrons to hop between, which is why I'm only seeing certain colors of my elements. Okay, so in lab this week we are going to do this. So in lab this week we are actually going to take various gases. So we'll have some hydrogen gas, we'll have some helium gas, I think we have some argon and some neon, and all different kinds of gases, and we're going to do this. We're going to take the gas in a tube and zap it, pass it through a little prism grating, and we're going to see the colors. And we're going to see then, the hydrogen's pattern is totally different from helium's pattern. It's totally different from argon or neon or whatever. This little unique pattern here that we get, this is important. This is called the atomic fingerprint. So every element has literally its own unique fingerprint. The atomic fingerprint. Now it's supposed to have a T on it, but you can't see it. Print. Okay. Well, why is it unique? Well, helium, for example, is going to have 2 protons now in the center. It's going to have 2 electrons orbiting. Right? So these levels then will be like a little bit different places. The attraction then is a little bit different. So it'll have a different pattern when it jumps back and forth. So one of the cool things this is used for then is NASA uses this. So what you can do then, you can take the light off some distant star or some distant planet or nebula, and you can pass that light then through a prism, and you can see the pattern it gives, and it says, aha, oh look, blue, green, red, must be hydrogen in that nebula. Or aha, it's the helium pattern, must be helium in that star. Or aha, it's the argon pattern. Whatever it is. Does that make sense? So like I said, so in lab this week, we'll actually do that, because we're going to actually take like 6 or 8 gases. We're going to zap their elements, pass them through a prism, and they're going to draw their different patterns. And then you're going to have an unknown one, which you won't know what it is, and you're going to so you have like 6 knowns, then you have an unknown then one, which you'll zap and you'll pass through a prism and you'll draw it and you'll find the one that it matches, and the one that it matches must be your unknown. Okay, so yeah.
Do isotopes change the colors that are emitted or no?
They do not change the colors. Why not, do you think? Because the isotopes only changes the what? Only changes the neutrons, which are here in the middle, right, and they're neutral. But this is all concerned with the positive attraction and the negative attraction. The rest of the neutral ones, in no effect. Yeah, good question. Okay, so that's how Bohr figured this out, which is why he won the Nobel Prize back in 1922. Okay, so we now know that yes, they do actually live only in certain orbitals, right? So it's not a big free-for-all. They're just wandering all over the galaxy wherever they want. They only live in certain places. So here's a cool picture. It's kind of cool to me. I was at the University of Copenhagen. After he won the Nobel Prize and stuff, they actually built what's called the Niels Bohr Institute, which is their physics department, named in his honor there. So it's 3 buildings. And the building right over here then to the right is where his office was. And it's kind of weird because he died, I don't know, he died like in, I think like 1960 or something like that. He died, a while back. But his office, though, is still the same way it was when he died. They left it as like a little shrine. So here's his office. So it's still the same desk and the same pictures on the wall and everything when he passed away. But kind of interesting, though, as far as the pictures that he had on his wall, though, kind of interesting. So he had various people of his heroes you might recognize here. So I don't know if you can see all these, but this guy, remember, this is on his wall. Rutherford, remember him? And this guy you probably know. Einstein, right? Different people like that. He had him there on his wall. It's kind of interesting. So, okay, so we now know that electrons, they hop only between certain energy levels, right? So again, it's not willy-nilly. They can't just go wherever they want and stop. They have to go from step to step to step and back. Okay, and as they get farther away, higher energy. Okay. Now, also what's true, though, is the higher the energy, well, the more electrons they will hold in that level. Okay, so let's say I'm in the first energy level, n equals 1. And I have electrons, and one more time, what's the charge on an electron? Okay, so if I put in electrons in the same orbital, what will they do to each other? because they're both negative charge. What are they going to do? They're going to repel each other, right? Okay. So as we get bigger, well, now I have a lot more room then for me to stuff in more electrons and still try to minimize the amount of repulsion. Are you with me? So right, they're bigger, so I can put more electrons in them as they get farther away and bigger. So they are higher energy, plus they hold more electrons, right? Because again, they're bigger, so they have more room to stuff them in. And again, the ones that are in there will have more energy too, right? Because they're higher energy. So these electrons in n equals 2 are higher energy than the electrons in n equals 1, we said. Okay. Okay, now within each level, there are also sublevels. And those sublevels are called S, P, D, and F. So within every level, there are actually little sub-regions of space, if you will, kind of, called S, P, D, and F. Okay? So the number of sublevels that an energy level can have is the same as whatever level you're on. So basically, if you're on the first level, you can only have one sublevel. If you're on the second level, you can have two sublevels. If you're on level 3, it's bigger, so we can have 3 sublevels. 4 can have 4, etc. So you can have as many sublevels, again, because it's whatever level you're on. So again, it's bigger, more room for all of this. So level 1 only has 1 sublevel. Level 2 has 2 sublevels. Level 3 has 3 sublevels. Level 4 has 4 sublevels. Yes, Aaron?
Since there's only 4 layers, when you get to the first level, you just like start to repeat the layers?
Yeah. That's a very good question. There are actually some other sublevels, theoretically, they're called GHI, but as far as though the known elements though, as far as the known elements though go, all we know about are ones that actually live in S, P, D, and F. But there is theoretically a 5th and a 6th and a 7th sublevel as well. We'll see. Because there are actually known right now, we actually know of 7 levels, but we only know of 4 sublevels. It's actually been, found, I guess, so far. And I'll show you where those live here in a second, actually, and then you can see for yourself where they come from. So, the first level can only have 1 sublevel, and it's the S one. The second one can have 2 sublevels, and it always goes in this order, an S and a P. The third can have 3 sublevels, an S, a P, and a D. The fourth can have 4. Let me draw. So the first sublevel only has a 1s. 2 can have 2. It could have a 2s. It could also have a 2p. 3 could have 3. A 3s, a 3p, or a 3d. And 4 could have 4. S is always first, and then p, and then d, and then f. So here's the level, the 1. Here's the sublevel, the s. So again, they're getting bigger, right? So bigger, so they have more room for more electrons, and they live in more diverse housing, in a sense. Yes.
Sorry, so you could have like level 3 could have 3 S's and 3 P's and 3 D's, or is it just you can have 3 S's or 3 P's?
A level 3 has 1s sublevel, which we call the 3s. Level 3 has 1p, which we call the 3p. It has a d, which we call the 3d. And the 4 has an s, we call the 4s. A p, the 4p, the 4d, and the 4f. There's still only one 4f sublevel. However, in the sublevel, see how there are little boxes? And the sublevels, those can even be I've broken down even further into what are known as the actual orbitals. So we have energy levels, and then within the energy levels are sublevels, and within the sublevels are orbitals. Aren't you thrilled? No? You're not thrilled? Oh, man. Okay. So orbitals then basically are the place where you have the highest probability of finding an electron. So you can do like some really complicated mathematics, and you can actually calculate, okay, where's the best probability of finding an electron? And those regions of space where you're most likely to find them, those are called the orbitals. Yeah. So you can go on into chemistry into a whole area, you can do all this high-level math called quantum mechanics. It's lots of calculus and crap. And you can actually calculate, okay, what's the move? Okay, where actually find the 4f electron or whatever. You can figure it all out. So, every orbital can hold 2 electrons. Two electrons.
Is that why they come in pairs? Like, in the sense of, like, you're on this level, you're on an energy?
Yes. You mean pairs like in here? Like
Yeah.
Yeah. Well, I mean, you can only have one if you want to, but they'll have, but there are pairs. You're right. So every orbital, so we have a level that has sublevels, and then a sublevel that has orbitals, and every orbital can hold 2. Confusing, huh? Let me try to explain that a little better. I'll use my patented apartment building analogy. Maybe I'll draw it on here so it'll be on here then, on the recording. Oh, we're out of time, aren't we? Ah, crap, Tastico. So we have I have like 30 seconds, so I'm going to tell you one thing real quick then, and I'll read it. So basically, think of it like this. Think of it like I have an apartment building, and it looks really weird like this. Okay? It's a very weird apartment building. So I have the first floor of the apartment, the second floor of the apartment, the third floor of the apartment, and the fourth floor of the apartment. Okay? 3 and 4. Now, the first floor only has 1 apartment in it. So that's your sublevel. It only has apartment 1S. Second floor has 2 apartments, apartment 2S and apartment 2P. 3 has 3S, 3P, and 3D, and 4 has 4 apartments. 4S, apartment 4P, apartment 4D, and apartment 4F. And within the apartments is the number of bedrooms in a sense. So which are the orbitals? Those are the orbitals, okay? So I will save that. I'm gonna actually have a little picture of that. I will save that, and we'll pick that up on Wednesday. So Wednesday, we've got a lab all about lovely electrons, right? So make sure you have your pre-lab, everything done. And then Monday, one last time, is going to be a quiz on Chapter 3, which we'll finish Wednesday. And a quiz off that green sheet of the polyatomic ions. If you don't have that green sheet, it's online on Blackboard. And it says on there, to memorize, polyatomic ions. So just make 10 flashcards. You'll know those by Monday.
Will you be uploading this videotape?
Yes, I will do it here.